Section 2, Understanding the Sun. There's an amazing amount that we do know about the sun, but I imagine there's a whole lot left to learn because it is so incredibly complex. What we have is the standard solar model, and a lot of, I think, students don't care for things that don't have a physical component to them. But even though this is a model on the computer, a mathematical model, what really counts is whether it makes predictions that we can observe. And the thing is, it does. Despite not having, we can't go drill into the sun. We can't get inside the sun and see how it works directly. But guess what? Based on the standard solar model, we make observations that fit the model almost perfectly. So we can feel very good about the model that we have. Now, one tool that we have, maybe the most important tool of all, is called helioseismology. Helio means sun, of course, and seismology, we normally think of earthquakes, but here we're talking about starquakes, or in this case, a sunquake. And when the sun does have seismic activity, it ripples through the sun, and we can study the waves on the surface. Let me show you what one of these looks like. Here's an amazing example.
This is actual footage of a sunquake.
Look at that. That was a very interesting example.
This is actual footage of a sunquake.
Let's try to pause it there. So, yeah, so that's how we study it. And if you think about it, we can't drill to the center of the Earth either. And yet we still know a lot about the interior of the Earth from earthquakes, from studying how those waves are affected, changes in frequency and intensity and so forth. So here's our sun through a filter. Guessing a hydrogen alpha filter in this case it's called. Pretty amazing. It really is so complex. And one thing you should immediately know about the sun, a lot of this activity you see is due to magnetism. I don't know why it's turning like that. I don't remember that video turning like so. But anyway, so we keep an eye on the sun at all times around the Earth. We have solar observatories. I'll sometimes go to the Big Bear website just to see if sunspots are out, so I know whether to take my class outside or not. Big Bear in Southern California. Looks pretty cool there on the edge of that lake. And McMath is an old one. I only mention it because I've been there and had the great opportunity to take a tour inside of it. I can tell you that that sort of sloped part is just like a big hollow tube. Light comes in the top, hits a mirror, shines right down through the tube to another mirror, which reflects the light down into a lab room, and it just comes out as a big circle of light on a table. Pretty neat stuff. On the sign-in sheet to get in, just a fun fact, all of the astronauts, Neil Armstrong and Buzz Aldrin, everybody from back in the day, had signed in there back when they were studying back in the 60s. All right. Not anymore. The best solar observatories are in space. We have the Solar Dynamics Observatory and Stereo, which I happened to see launch just on accident one night driving here in Florida. I happened to see when they were launching Stereo. Stereo, just like you think of a stereo being left and right speakers in an old-fashioned stereo, this is what this means as well. They work together. They can take 3D images of the sun. The SDO, which is an amazing spacecraft, I mean, it has all kinds of different filters. It's located at the Lagrange point between the Earth and the Sun. I think that's the L1 point between the Earth and the Sun. So it rides along always between us and the Sun, so we can watch the Sun 24/7, if you will. And then look at this. Stereo, those spacecraft actually travel with the Earth, one in front and one trailing the Earth, I assume at Lagrange points as well. And so, like I mentioned, they can work in tandem and actually take 3D pictures and stuff like that of our sun. So let's talk about the inside of the sun here for just a moment. The core is where the action is. That's where it's important. That's where the fusion takes place. That's where the sun creates energy, or better said, converts mass into energy. And turns out that in order to do that, you need to be at a pretty hot temperature, as you can imagine. Our sun clears the bar at 15 million Kelvin, probably roughly 30 million degrees Fahrenheit. Much, 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 much hotter than the surface. Remember, the surface is only like maybe 10 or 12,000 degrees Fahrenheit. The core is also different than the rest of the sun because it is so much denser. The density of the sun drops off amazingly after the core, but at that point it's actually denser than iron, even though it's not a solid. Even though it's not solid, it's still denser than iron. It's just too hot to actually be a solid, even despite the density. Now, according to Mr. Einstein's equation back in 1905, the famous E equals mc squared, if you take 1 kilogram, that's the m, and you multiply times c squared, that's the speed of light, which is a big number, and you square it, 3 times 10 to the 8 squared, you get 60 trillion joules of energy from 1 kilogram, from a couple pounds of material. It's an amazing amount of energy from mass. That's what E equals mc squared simply means. You get a whole lot of energy from a little bit of mass when you make that conversion. There it is, E equals mc squared. Just a short little lesson on that. Now, specifically, what kind of fusion are we talking about? Well, we're talking about the fusion of protons. So it's sometimes just called proton-proton fusion. And the key temperature, if you want to try this at home, don't try this at home, 10 million Kelvin. So our sun, again, is at 15 million Kelvin. We have that bar cleared easily. So here's what happens. You're talking about throwing 2 protons together. Now remember, this is hydrogen without its electron. That's all it is. When we talk about fusing hydrogen, we really just mean fusing protons. And the basic thing you learn about protons in elementary school is what? That they are positively charged. So if you throw 2 positive things together, what do? Oh, they repel. Let's watch the low speed. 2 protons, no, they're going to repel each other and not collide. Unless they are moving so fast because it's at such a high temperature, 10 million Kelvin, that they do this. Bam! They actually fuse together. So, at that point, if the protons get close enough, a new force of nature takes over called the strong force, which, as you can imagine, is stronger than the electromagnetic force, which is the opposites attract and likes repel. That's not quite true. If you can get the 2 objects close enough together at a high enough temperature, then the strong force takes over and they bind together. All right. So that's nuclear fusion. That's the most basic type of nuclear fusion, proton-proton fusion. Here is the full reaction that takes place in the sun. It's a little more complex, as you can see, is just saying, oh, hydrogen plus hydrogen equals helium. You have a lot of in-between steps, and you have some important things happening here along the way. You notice in the end, you end up actually fusing 4 protons, or hydrogen, to make 1 helium nucleus. What you actually end up with, the 4 protons actually end up being 2 protons and 2 neutrons. Now, all a neutron is a proton and electron fused together. So there are 4 protons there. 2 of them are kind of hidden as neutrons. But along the way, lots of interesting stuff happens. You notice you have energy given off in the form of gamma rays. That's your energy being released. And something else important, you have something called neutrinos given off. You have, anyway, I don't want to get into detail here of all the reaction, but that's the basic, that's the reaction that takes place in our sun and in lots and lots of stars. There are more advanced forms of fusion that occur in the more massive stars, but this is the bottom line. You start with 4 protons, you end up with a helium nucleus plus energy plus neutrinos. And what happens is that the original 4 protons literally weigh more than the helium nucleus. There's missing mass. It's just a small percentage of the mass. But that mass, where has it gone? It has become energy. That's what E equals mc squared predicted and shows that little bit of mass becomes energy. That's where the energy of stars and our sun comes from. And then it also releases neutrinos. Now, for a while, there was a problem called the neutrino problem, where we weren't seeing as many neutrinos as we thought we should. When I started teaching, this was a big, big mystery. They think they've solved it. They think there are actually different types of neutrinos, and we were only detecting about 1/3 of the number because we weren't looking, they sort of come in different flavors, and we were looking for, vanilla neutrinos, and there were actually other types. They're called things like tau neutrinos and so forth. But anyway, how do you find these neutrinos? These neutrinos are ghost-like particles. They're incredibly hard to detect. Most of the time they pass right through your body and right through the entire Earth and hit nothing. That's how small they are. They hit nothing. So we have to go to great lengths to detect even one of them. Here's an example of a neutrino detector in Japan. That's water. It's actually called, it's what's called heavy water. And that's a raft out there. And this is deep underground, to where the only thing that can get down that deep through the earth without hitting anything is a neutrino. And every once in a while, a neutrino will hit a molecule and actually release energy, and then these bulbs light up, I guess, and show that a neutrino was there. Here's one without the water in it. Here's an interesting one in Antarctica, which is also a neutrino detector. I think it's called the ice cube or something like that. Pretty cool. Very important graph here. This shows how much energy you get from nuclear reactions. Let's actually start on the right side very quickly here. What we do on the Earth is fission. We do nuclear fission. Even right here in South Florida, in Miami, at Turkey Point in Miami, we have a nuclear reactor. And that's where you take really big, heavy atoms that seem like they're ready to fall apart, things like uranium and plutonium, different isotopes of them. And you can split the uranium, and the steepness of the slope represents sort of how much energy you get. When you split the atom, you're going to get different atoms and you're going to get energy released. That's the fission side. The fusion side, look at this. When you start here with hydrogen on the left and you go to helium, the change there, that change in energy is showing you how much energy you get per reaction. So hopefully you can see there from the sort of the steepness of each side that you get a lot more bang for your buck from fusion than from fission. That's why if we ever master fusion, we'll have enough energy forever. Not to mention the fact that uranium is very scarce and hydrogen is all over the earth. I mean, we are covered in H2O. One more interesting thing here is at the very top of the hill, you have an element that in nature does not want to undergo fission or fusion. And we'll talk about that element a lot later in other chapters, but that's iron. That's iron. We'll get to that later. Here's an actual fusion reactor. Yeah, they actually exist. We can actually do fusion. And the way we do it is we put some protons here at the end of this, looks like a pencil, and they actually have, in this case, they have a bunch of lasers that shine in on it and actually are able to fuse them together. There's one tiny little problem, and that is they use a whole lot more energy powering the lasers and stuff than they get from the reaction of fusing the protons. So we're nowhere even close, apparently, to having a sustainable fusion where we could actually get energy from it. We're not there yet. And it seems like we're always 20, 30 years away. That's kind of the joke. We're always 20, 30 years away. I guess there is one exception. I have seen one time when we were able to produce sustainable fusion. Let's take a look. Oh, there it is.
Doctor, we have a successful fusion reaction.
This is a breakthrough beyond your father's dreams.
Thank you. We're producing 1,000 megawatt surplus.
All right, so Doc Ock figured out in Spider-Man 2 how to get a surplus from nuclear fusion, but he's ahead of us because we haven't mastered that yet. Anyway, we'll talk about how that energy from the core makes its way out of the sun next time. Thanks for listening.